You know that feeling, right? You're working on something important, tapping your fingers on the desk, just waiting for that little spinning wheel to disappear. Of course you do. It's universal. This feeling that our tech should just be faster. So let's get into it and figure out why this race for performance never, ever seems to end. First, to really get where we're going, you have to appreciate just how far we've come. I want you to think about this for a second. The laptop sitting in front of you, the one you might be watching this on, it has the same raw computing power as a gigantic room-filling mainframe computer from the 90s. The amount of progress it's just mind-boggling. So how did we get to this point? And what's the next big hurdle? Well, in this explainer, we're going to break it down into 4 key parts. First, we'll look at our never-ending need for speed. Then, we'll get into the high-speed balancing act that's happening inside your computer right now. After that, we'll cover the clever tricks engineers use to squeeze out every last drop of performance. And finally, we'll tackle the big one, the multi-core challenge. Okay, let's start with the most basic question of all. Why are we so obsessed with this stuff? Why has performance become probably the most critical part of computing? Honestly, the answer is pretty simple. It's what we're doing with our computers. We're not just typing up documents anymore, are we? We're editing high-res photos, rendering 3D models, talking to our devices, jumping on video calls all day. All of this stuff, which is now just part of our everyday lives, it takes a massive amount of computational horsepower. Basically, our ambition for what software can do is what keeps pushing hardware to be faster. So you might be thinking, okay, just make everything faster, problem solved. Well, if only it were that easy. This brings us to the real core problem inside every single computer, this incredibly tricky, high-speed balancing act. Here's the key thing to understand. Your computer isn't just one thing. It's more like a team of specialists. And like any team, its performance is totally limited by how well they all work together. The big problem? The members of this particular team work at wildly different speeds. Think of it like this. Your processor, it's an Olympic sprinter. It's blazing fast, running billions of operations every single second, and it needs data right now. But your memory and storage, they're more like a very careful, very meticulous librarian. They have all the information you could ever want, but they gotta walk down the aisle, find the right shelf, pull the right book, and then walk it all the way back. All while the sprinter's just standing there, tapping its foot, waiting. And this chart, wow, this really just lays it all bare. You can see the processor's speed is way up here, just through the roof. Then you've got main memory, which is a lot slower. And the hard disk, it's barely even on the chart, just crawling along in comparison. This huge mismatch has been the single biggest bottleneck computer architects have been trying to solve for decades. So, to deal with this, engineers got really creative. They came up with all sorts of clever architectural solutions. Things like caches, to cut down on those trips to the library. They built wider, faster highways for data to travel on, called buses. And they designed ways to grab bigger armfuls of data at once. It was all about trying to get the team to work better together. Okay, so if the team is always going to be a little unbalanced, how did we make that sprinter even faster? Well, that brings us to part 3, squeezing out more performance. Let's look at the incredible bag of tricks engineers use to make a single processor work smarter, not just harder. One of the absolute biggest tricks in the book is something called pipelining. The idea here is brilliant. You make the processor work like a factory assembly line. Instead of taking one task from start to finish before even looking at the next one, you break each task into small stages. That way, a new task can start as soon as the first stage of the old one is done. So just think about it. While one instruction is being executed, the very next one is already being decoded, and the one after that is being fetched. Every single part of the processor is kept busy, all the time. This massively increases the total number of instructions you can get done. It's a huge deal. But what happens when the code has to make a choice? Like an if this, then that kind of thing. The pipeline could stall, so the processor basically becomes a fortune teller. It uses a cool technique called branch prediction to make a really, really good guess about which way the program's going to go, and it starts working on those instructions before it even knows for sure. If it guesses right, which it does most of the time, it saves a ton of time. And remember our slow librarian? Well, caches are the answer to that problem. A cache is a tiny, super fast chunk of memory that lives right next to the processor. It's literally like keeping your favorite, most used books right there on your desk, instead of having to walk all the way back to the library every single time. It's an absolute game changer for cutting down that wait time. For years, these tricks, plus making transistors smaller and smaller, gave us these incredible speed boosts year after year. But then we hit a wall. And I mean a very real physical wall. Pushing for more speed just started generating so much heat that the chips were literally in danger of melting. The tiny wires inside got so small and so close together they started interfering with each other. And our librarian, memory, it just couldn't get any faster to keep up with the sprinter. Hitting this wall forced a complete change in thinking in the entire industry. And that brings us to our last section, the multi-core challenge. The new philosophy became, if you can't build one thing that's faster, well, just build more of them. The logic was actually pretty simple. If one super fast brain has hit its physical limits, what do? Why not just use 2 brains, or 4, or 8, and have them all work on the problem at the same time? And that is precisely what happened. The industry pivoted and started putting multiple independent processors, what we now call cores, onto a single piece of silicon. The dual-core and quad-core chips in your phone and laptop, they were born right out of this moment of crisis. But, and there's always a but, this amazing hardware solution created a massive new problem on the software side. And this problem is perfectly captured by something called Amdahl's law. It's basically a formula that shows you the best possible speedup you can get by throwing more processors at a problem. And what it shows is kind of a harsh truth. Take a look at this graph. It shows that even for a task that is 95% parallel, which means 95% of it can be split up among multiple cores, the speed up starts to completely flatten out. See that? After maybe 16 or 32 cores, adding more and more just doesn't really help you much. Why? Because the whole system gets bottlenecked by that last 5% of the job that just has to be done in order, one step at a time. And this leads us to the new reality of computer performance, which is summed up perfectly by this quote. The hardware folks did their job. They gave us all these cores. But to actually use them, to get that power, this software itself has to be completely rewritten to think in parallel. And that's where we'll end it. You see, for decades, the race for performance was all about hardware, faster clock speeds, clever tricks, smaller and smaller transistors. But now, the path for hardware is kind of simple. Just add more cores. Which leaves us with a really fascinating final question. Is the great performance barrier of our time no longer about the silicon at all, but about the code that runs on it?